So my name's Joe, and this is joint work with Noah Johnson and professors Joe Hellerstein and Dawn Song at UC Berkeley. And we've had a lot of great help on this project from Minotti Minutelo and the whole Uber privacy engineering team. So I especially want to thank them. So this is a talk about data privacy, okay? What we'd like to be able to do is utilize data. We want to learn from it, while at the same time protecting the privacy of individuals. So what do I mean by that? On the left here is a query, how many trips were taken in New York last year, that reflects a trend over the whole population, okay? The answer to this query is not reflective of any individual person who took a trip in New York. It's reflective of the whole population. On the right side is another query, how many trips did Joe take last week? And the answer to this query is influenced by only one person's data, mine, okay? So if I took no trips last week, then the answer to this query is very different than if I took 25 trips. And so what we'd like to be able to do to solve the problem of data privacy is to allow queries like the one on the left, whose answers reflect trends in the population, and disallow queries like the one on the right that reflect properties of a specific individual and might violate his or her privacy. So the thing I want to point out here is this is not a security problem, okay? You can't write an access control policy that will solve this problem. So the problem of data privacy really is a distinct issue that needs its own solution. I want to give some examples of how these privacy risks can come up. So one category is internal risks. Oftentimes organizations will have analysts internally that need access to data in order to do their jobs. But the risk is that they could abuse that access, and then you get insider attacks. And we've seen lots of examples of those. Another category is external risks, in which organizations are sharing data, either with other organizations or with governments or the public. And the risk here is that organizations may be sharing more than they intended, okay? So it may be possible to go from data that seems to be safe back to identities of people in that data set. And I'll talk about an example of this in the Netflix Prize in just a minute. So the challenge in our research is to protect the privacy of individuals for both of these kinds of use cases. And we'd like to do it while allowing general purpose data analytics. So we'd like to be able to do the same kinds of analyses of the data that we're doing today. So here's an outline of the talk. So I'm going to first talk about differential privacy and what it is and why it's a good framework for thinking about solutions to this problem. And then I'll talk about why differential privacy is not used more in practice. So what are the challenges that are preventing its adoption? And finally, I'll talk about Chorus, which is the system that we've been working on that enables privacy-preserving data analytics in the real world. So it addresses all of those challenges. Okay, so what are people doing today to solve this problem? Typically what they do is anonymization. Okay, if you take the names out of the data set, then you can't figure out who's in the data set, right? Anonymization, though, has a couple of big problems. And the first one is that it limits utility. If you take identifying information out of the data set, then there's less data, right? And in fact, that can mean that you can't learn as much from the data. But perhaps the bigger problem is that it doesn't work to solve the problem of data privacy. So anonymized data sets are typically subject to re-identification attacks, where you link the anonymized data with another data set that has identifying information. And you can recover the identities of people in the anonymized data set. And there's lots of examples of this too. Probably the most famous one is with the Netflix Prize data, where some researchers were able to take the Internet Movie Database data and recover the identities of Netflix customers. And Netflix actually canceled the follow-on contest because of these privacy issues. Another example that is slightly less well known, but this is one of my favorites, is with the New York City taxi data set. And this is an anonymized data set of taxi trips. And Anthony Tucker was able to take this data and combine it with photographs from celebrity gossip websites and figure out which of the trips in the taxi data set corresponded to trips that celebrities took. And so he was able to figure out where they went and how much they paid and how much they tipped. And what I like about this one is it's so surprising, right? Who would have thought you would combine taxi data with celebrity gossip photographs? And the lesson here is that there is all kinds of data out there. And if you're publishing an anonymized data set, you don't know what other kind of data might be out there that could be linked with it. And in fact, somebody might come out with a new data set in 10 years that could be linked with your data set and compromise the privacy of the people in it. So differential privacy is a totally different approach. It's not a procedure, it's a definition of what privacy means. Okay? So differential privacy gives you a formal mathematical definition of what it means to have privacy. And then you can design algorithms, which are typically called mechanisms, that you can prove give you this property. So I'm going to try to give you an intuition for what the differential privacy guarantee actually gives you. So imagine you have an analyst who's posing a query on a database and they get an answer. In this case, the analyst is kind of like the adversary. The analyst is trying to figure out something about an individual, say me. If the analyst is posing a query on this database, now imagine we have a second database that's identical to the first one. The only difference is my data. So the first database does not have my data, the second one does. If we pose the same query on both databases and get two different results, differential privacy says that these two answers have to be very close to equal. So what that means for me as the person who's considering whether or not to contribute my data to these databases is if these two answers are very close, then the analyst, the adversary in this case, can't tell which database was used to run the query. So that means they can't tell whether I was even in the database. And if the analyst can't tell whether my data was in the database, then I'm going to get the same outcome. The analyst is going to make the same decision, and the same thing is going to happen to me whether or not I contribute my data. And this turns out to line up really well with what we want from privacy. We want to make sure that bad stuff doesn't happen to us because we contribute our data. All right? So that's differential privacy. You can write it formally in terms of probabilities. One thing I'll mention that's a technical detail that'll pop up later in the talk is that there's a parameter to the guarantee that differential privacy gives you called epsilon. And it's often also called the privacy budget. And it's basically a number that tells you how strong is the privacy guarantee that you get. Okay, so differential privacy gives you this great guarantee. Why don't people use it more? There's been a ton of theoretical work on differential privacy. We know a lot about what you can do with privacy. And there's been some examples of very specialized systems that are deployed in the real world that have differential privacy. But these are very specialized. If you wanted to apply them to more general analytics tasks, you'd have to rewrite the system. And so the result is there aren't any deployments of differential privacy for general purpose analytics tasks. And we've identified kind of three main challenges that are standing in the way of doing this. The first one is usability for non-experts, right? We don't want the analyst to have to know anything about differential privacy. The second one is broad support for analytics queries. So we want to support all the kinds of queries that people are running today. And the third one is easy integration with existing data environments. So it's got to work with a database you already have. And there aren't any systems that do this, right? No system supports all three of these. So I want to give a couple of examples of why this is hard. So with the issue of broad support for queries, this is a list of just some of the differential privacy mechanisms that exist. And these are some of the more general purpose ones. And each one of them has specific strengths. So it works well for certain queries and not so well for other ones. And so what this means is, in order to have broad coverage for queries, we need a system that can deploy multiple mechanisms, okay? But existing systems typically give you just one. On the issue of integrating with existing data environments, so this is just kind of a snapshot of some of the databases that are used at Uber. And you see that there's a bunch of them. Each one of them is tuned for a specific task, right? It's put in deployment for a specific reason. And so that means we really need to be able to support all these different databases, okay? But typical systems for differential privacy actually require changing the database or replacing it completely with a new database that executes the query in a different way. And so that's just not going to work in a data environment that has so many different database engines. So Chorus is a framework we've been developing for enabling privacy-preserving data analytics in the real world by addressing these challenges. So Chorus is usable by non-experts. The analyst doesn't have to know anything about differential privacy. Chorus automatically enforces differential privacy for regular SQL queries. So the analyst gives a SQL query like they're used to writing, and they get back a differentially private answer. Chorus has broad support for analytics queries. So it's designed to be very modular so that we can support lots of different differential privacy mechanisms in one system. And with just the ones we've implemented so far, we've been able to support about 93% of queries in a workload at Uber. It provides easy integration with existing data environments. So you can use it with a standard SQL database. And I'll speak more about this in just a second. So Chorus is really designed for these real-world deployments that so far haven't happened. Okay? It's actually plans for deployment are underway today at Uber. And so Chorus really is designed to solve the challenges that come up when you're trying to deploy this stuff in the real world. So what's different about Chorus that allows us to do this? Chorus takes a completely different approach to enforcing differential privacy than any previous system. So previous systems, typically, they change the way the database works so that the database gives you differential privacy. Chorus doesn't change the database, it changes the query. Okay? So Chorus is actually a query rewriting system. It takes in the query that the analyst writes, and it produces a query that we call an intrinsically private query. And the intrinsically private query has a differential privacy mechanism embedded in it. So that the query, when you run it on a regular database, will enforce differential privacy on its own results. All right? And so you can, just like on the picture on the bottom here, you can have an analyst write a query, it goes into Chorus, and out comes this intrinsically private query. And now you can run that on any database you want, like the one you already have, and you'll get differentially private results out. And those can go directly back to the analyst. You don't have to do any post-processing or anything else to those. And so this is a big win over what we had before, because it means we don't have to change the database at all, or the data. It works with any standard SQL database. So I want to give you a couple of examples of how this works for actual differential privacy mechanisms, how we can rewrite the query to embed the mechanism in the query. And I'm going to start with one, I'm going to give two examples. I'm going to start with one called elastic sensitivity. And this is actually a differential privacy mechanism that we developed at UC Berkeley about a year ago. And it uses a kind of traditional approach to getting differential privacy. That is, you first run the query on the database and you get a sensitive result, one that's not private. And you add some noise to it. And you add enough noise that the answer you get after the noise is added is differentially private. Okay? And this was one of the first strategies developed ever, more than 10 years ago now, for getting differential privacy. So it turns out if you add this noise drawn from the Laplace distribution, you get differential privacy, assuming that the noise's scale is equal to the query's sensitivity. So how much noise you have to add depends on the query. Okay? And that makes sense because some queries are kind of more sensitive to the information of an individual than other queries. And so the big question with this approach is, how do you know what the sensitivity of the query is? And elastic sensitivity is precisely an approach to answer that question. It's an efficiently computed upper bound on the query's sensitivity. And what's different about elastic sensitivity compared to approaches that came before it for this is that it supports joins, which turns out to be pretty complicated. So we have a completely separate paper on this approach if you're interested in the details of that. So what I want to show you is how to implement elastic sensitivity as a query rewriter. So this is the way we do it in Chorus. It looks something like this. So the boxes in this picture represent chunks of SQL that are kind of hiding behind the boxes. Okay? So on that second line, there's a blue box that says original query. That represents the actual SQL query that the analyst wrote, the input to the Chorus system. Okay? So to get an intrinsically private query that gives you differential privacy using the elastic sensitivity mechanism, what we want to do is first run the original query. So that's why we're selecting from the results of the original query. We want to select the original column, the same one that the analyst was selecting in his or her query, the original query. And then we want to add to that result this noise drawn from the Laplace distribution. And we scale that noise according to elastic sensitivity and according to the privacy budget. And Chorus can automatically determine what that scale should be, what the elastic sensitivity of the query is, by doing a data flow analysis of the input query. So I want to show you what that actually looks like on a real query. This is about the simplest query you could imagine. Select count star from trips. So this is literally asking the question, how many trips are there in the database? So we put this into Chorus and we get a query that looks like this. It says select count star plus 1 over epsilon. So that is the scale of the noise we need, because the sensitivity of this query is 1, and the privacy budget we're using here is, I'm just putting the kind of placeholder epsilon here for that. And then some arithmetic, right, some stuff. And that stuff gets the Laplace noise and asks it's actually generating Laplace noise from the randomness that the database engine gives you. So you can see there's a couple of calls to the rand function in there. The rand function can give you random noise from the uniform distribution, and the arithmetic that we're doing here converts it into random noise from the Laplace distribution. Okay? So we have this intrinsically private query, and you can run this on a regular SQL database and get differentially private results. The second example I want to show you is called sample and aggregate. And this one is very different from the last one. And so I want to show you this one because it really demonstrates the flexibility of Chorus to accommodate different kinds of differential privacy mechanisms. So sample and aggregate supports statistical estimator functions like average, which is nice because these are the kinds of functions that actually elastic sensitivity doesn't support. But it requires significant changes to how the query executes. So the traditional way to implement an algorithm like this is to replace the database with something that does something different. So I'm going to give you an intuition of what the algorithm does. The first step is you take your database and you split it into partitions. Okay? And then you run the original query on each partition separately. So you get a bunch of answers, one per partition. And then you aggregate the partitioned answers using a differentially private aggregation function. And you get differentially private results. So the intuition here is if there's an outlier, an individual in the database who's very different from all the other ones, we're going to protect that person's privacy because that person ends up in one of the partitions and they affect the answer to the query on their partition by quite a lot. And so that answer is going to be very different from the answers on the other partitions. And so if we add noise at the end, scaled to the difference between the minimum answer on any partition and the maximum answer on any partition, then we can ensure differential privacy. So this mechanism essentially is calculating the sensitivity of the query on the fly as the query executes. So how do we do that as a rewriter? So the first step, remember, is to partition the data. So first what we can do is we can run the original query and group by what we call a partition expression that generates those partition numbers. And then we need to calculate what we call the interquartile range. And this is essentially the difference between that maximum and minimum that I just talked about. And we have to do that privately because that number can leak information about the data. So we have an algorithm for that that's specified by sample and aggregate. It's too big to show here, but it's just arithmetic. So you can implement that in SQL. And the nice thing is that that doesn't change. It's the same for every query. So the rewriter can just stick the definition, can inline the definition of that algorithm into the query. We're going to do the same thing for the actual averaging. We use an algorithm called Windsorized mean, which clips outliers and then takes the average. And again, there's an algorithm that essentially you just implement once, and then you inline it to every query that uses the mechanism. And then at the end, we're going to add noise to that average that we've got, scaled to the effective sensitivity of this query, which we can get from the interquartile range. Okay? And that's it. So the query, I'm not going to show an example of this one because it won't fit on the slide, right? The SQL that we generate is actually pretty big. But conceptually, it's very simple. It follows the structure of the algorithm almost exactly, okay? And so by implementing differential privacy mechanisms this way, by rewriting the query, we actually have a whole lot of flexibility as far as what kinds of mechanisms we can support. And we've looked at a bunch of different mechanisms, and we have yet to find one actually that we wouldn't be able to support this way. So the next obvious thing for us to do as researchers is to run some experiments, right? We now have a system that will let us look at the differentially private answers to real-world queries. So we did that, and this is actually the first experiment of this type because we have the first system that can run these differential privacy mechanisms on these queries. So we looked at about 19,000 SQL queries that were written by analysts at Uber, and we asked things like, how good is the accuracy? How good is the utility of these results? How big is the noise compared to the answer? And are the answers accurate or not? For elastic sensitivity, and we tried these for other mechanisms as well, the results differ a little bit, but they follow the same basic trends. For elastic sensitivity, we found that we can get less than 1% error in the answers for a majority of the queries in this workload that query reasonable population sizes, okay? So for queries that people are already writing, we're able to give very accurate answers for a lot of those queries. In terms of performance overhead, each rewriter is going to have a slightly different effect on the performance of the database, but for elastic sensitivity, we see very low overhead. So it's about a 1.7% median overhead, and that's on a database of about 800 million records. And we also found that supporting multiple mechanisms really increases the set of queries we can support. So we've implemented 4 so far, and that gets us up to almost 94% of queries in the workload. So to wrap up, Chorus is really the first framework that enables practical differential privacy for this broad range of general purpose analytics queries. So we've addressed these 3 challenges that I talked about. It's usable by non-experts, it provides broad support for analytics queries, and it integrates easily with existing data environments. And we've seen in our experiments that the supported mechanisms can provide high accuracy and performance for a lot of the queries that people are writing today. So I want to encourage you to take a look at a blog post that the folks at Uber have written about the details of their system. And I want to encourage you to download the code that we're releasing today for Chorus. And this is especially exciting to us because we love to get feedback on the code. And we're especially interested to hear about potential use cases that you all may have and potential interest in actually deploying Chorus. And so if you have any of those, we'd love to talk about it. So please come find me afterwards or send us an email. We'd love to talk more. So I'll leave it there. Thanks very much. And I'd like to actually invite my co-author, Noah Johnson, on stage for the question and answer section.